Hi, my name is Andrea Rudd from PEO4. Today, I will be showing my medical electronics project demonstration. Before we start talking about our signal processing circuit, I would like to talk about the heartbeat acquisition system as a whole. So the block diagram represents a single processing circuit designed to amplify and filter the acoustic output of the stethoscope for clearer listening through a speaker. We start off at this stage first, the stethoscope and acoustic output. This is where the sound of the patient's heartbeat is captured by the stethoscope. We move on to the next stage, where the microphone picks up the acoustic signals from the stethoscope and converts them into electrical signals. And the preamplifier amplifies the weak electrical signals from the microphone to a higher level for further processing. This step is crucial because the initial signals are usually too weak to be directly processed or heard clearly. The low-pass filter allows low-frequency signals, such as the low-frequency components of the heartbeat, to pass through while reducing higher-frequency noise. This filtering is important to remove unwanted high-frequency noise that may interfere with the healthcare worker detecting a clear heartbeat sound. Lastly, of the single processing circuit, the audio amplifier further amplifies the filtered signal to a level that can drive the speaker. The line-out gain control adjusts the amplitude of the signal, which affects the loudness of the sound produced, allowing for volume control to ensure the heartbeat can be heard clearly through the speaker without distortion. And at the last stage of the heartbeat acquisition system, the final amplified and filtered signal is sent to the speaker, which converts the electrical signals back into sound. This allows the healthcare provider to listen to the patient's heartbeat clearly and loudly enough for accurate diagnosis. This is my patched up circuit for the signal processing circuit. We now start at stage 1. This is the schematic diagram for the microphone preamplifier. I'll be touching on PG203J, which is the microphone or stethoscope sensor. Basically, this is the start of the heartbeat acquisition system. It picks up the sound of the heartbeat and converts it into electrical signals. By when a doctor places the stethoscope on a person's chest, this sensor detects the tiny sounds of the heartbeat beating. We now move on to the voltage divider, R5 of 10k ohms and R6 of 10k ohms. It provides a bias voltage to the non-inverting input pin 3 of the operational amplifier TL072. It turns a large voltage into a smaller one. We can calculate the Vout voltage in this way. To calculate Vout, we take Vin times R6 over R5 plus R6. Our Vin is 9 volts. So 9 volts times 10k ohms over 10k ohms plus 10k ohms, which gives us 4.5 voltage. Now, the voltage divider, the 4.5 bias voltage ensures that the op-amp operates correctly. It centers the input signal around the midpoint of the supply voltage, allowing the op-amp to amplify both positive and negative variations of the inputted heartbeat signal. It acts as a level shifter to shift the entire waveform upwards, so it would not be cut as the input voltage was 9 volts. Moving on to capacitor C1, the input capacitor C1 blocks any DC component from the microphone, ensuring only AC signals such as the heartbeat sounds to reach the non-inverting input. With the bias set by R5 and R6, the op-amp can properly amplify the AC signal centered around 4.5 volts. Without the VD and C1, the op-amp might not work correctly, and the heartbeat sound could be too weak or distorted to hear properly. We now move on to IC1A. It is a fixed-gain closed-loop operational amplifier. Below it is R2, R3, C2, and C3. They form the band-pass filter. R2 and C2 form the low-pass filter, allowing low frequencies to pass through. R3 and C3 is the high-pass filter, allowing high frequencies to pass through. This allows only a specific range of frequencies to pass through and discarding all other frequencies. The formula is given by 1 plus R1 RF over Rin. Hence, subbing in the values, the gain will be 1 plus R2 over R3, which equals 1 plus 220 kiloohms over 10 kiloohms, which gives the maximum gain of 23. Lastly, capacitor C4. It acts as a coupling capacitor, coupling the output of IC1A. If there is any DC frequencies at the output, it will increase the output till it is too large and cause it to be cut. It isolates the DC signal and only allows the AC output signal to pass through. We now power up the circuit with 9 volts and connect channel 1's probe to test point 1 and channel 2's probe to test point 2. We also put the function generator at the start of the circuit before capacitor 1. With the function generator frequency set at 100 Hz with an amplitude of 200 millivolts, our channel 1's reading will be 218 millivolts and our channel 2's reading will be 4.72 volts. At a frequency of 1 kHz and 200 millivolts for amplitude, our channel 1's reading will be 216 millivolts and our channel 2's reading will be 3.36 volts. From my readings, I have tabulated my results from 10 Hz all the way to 4 kHz. And as the frequency increases, the gain also increases until it reaches a certain point. It should reach around a maximum of 23 based on what we calculated from earlier. The maximum gain I got was 22.4 at a frequency of 100 Hz, giving me 27 decibels. After getting our values, we can draw a frequency response curve to get our lower cutoff frequency and upper cutoff frequencies. To do that, we take 27 decibels, which is our max gain, minus 3 decibels, which will give 24 decibels. The lower cutoff frequency will be this point here, and the upper cutoff frequency will be this point here. So our lower cutoff frequency will be 17 Hz, and our upper cutoff frequency will be 1.2 kHz. To find the bandwidth, we take the upper cutoff frequency minus the lower cutoff frequency, which will be 1183 Hz. Hence, the high-pass filter R3 and C3 removes low-frequency noise, such as movement artifacts or breathing sounds below 17 Hz, and the low-pass filter R2 and C2 remove high-frequency noise, such as electronic interference or ambient noise above 1.2 kHz. We now move on to stage 2. At stage 2, this is the continuation of the microphone pre-amplifier circuit. IC1B shares the same ICTLO72 with IC1A. It is a negative feedback closed-loop amplifier where it returns the output back to the input after a fraction of it is subtracted from the input, with a 180-degree out of phase. There is a second voltage divider. Now this voltage divider consists of R9 and R10 connected to pin 5. Similar to the first part, the Vout will be 4.5 volts. Hence, it acts as a level shifter to shift the entire waveform upwards, allowing the output to not be saturated. Trimmer port P1 controls the feedback signal, reducing the gain of the amplifier so that the output voltage can be adjusted to not be saturated, ensuring that the amplification can be fine-tuned to avoid distortion. This ensures that the heartbeat sound is detected and amplified strong enough for subsequent processing or listening. Finally, we test the output at test point 3. We now connect channel 1's probe to test point 2 and channel 2's probe to test point 3. The function generator is still kept at the start of the circuit in front of capacitor C1. Keeping the frequency at 1 kHz and 200 millivolts for amplitude, by adjusting P1, the output waveform will be amplified but saturated and cut off at a certain point. We now move on to stage 3. At stage 3, this is the low-pass filter schematic diagram. Capacitor C5 is similar to the capacitor at C1, which is to block DC signals and allow AC signals to pass through. Voltage divider R11 and R12 also work similarly as the previous voltage dividers, where the output voltage is 4.5 volts. The voltage divider acts as a level shifter to single supply voltage to ensure output voltage is not saturated. IC2A is the same IC as IC1A and IC1B. It is a Salem-Key second-order low-pass filter made with two low-pass RC networks. It allows low frequency to pass through while filtering out high frequencies. We move on to capacitor C7. It provides feedback for shaping the response near the edge of the pass band. And capacitor C8 is similar to other coupling capacitors such as C1 and C5. It ensures only the AC signal, which is the heartbeat sounds, to pass through to the next stage, blocking any DC signals. At this stage, we now remove the function generator and place it at test point 3 before capacitor C5. Channel 1's probe is now connected to test point 3 and channel 2's probe is connected to test point 4. At 50 Hz and an amplitude of 5 VPP, our channel 1's probe is 5.04 volts and our channel 2's probe is at 5.04 volts. At a frequency of 100 Hz and an amplitude of 5 VPP, our channel 1's probe is at 5.28 volts and our channel 2's probe is at 5.20 volts. At a frequency of 500 Hz and an amplitude of 5 VPP, our channel 1's probe is at 5.04 volts and our channel 2's probe is at 3.12 volts. At a frequency of 1 kHz and 5 VPP, our channel 1 input is at 5.04 volts and our channel 2 input is at 2.56 volts. At a frequency of 2 kHz and 5 VPP for amplitude, our channel 1's input is at 5.04 volts and our channel 2's input is at 920 millivolts. After tabulating my results in this table, we can see that from 20 Hz to 100 Hz, the input voltage is very close to the output voltage. Hence, the gain is a unity of 0 decibels. This means that the filter allows this low frequency range to pass through without any reduction in them. When the frequency reaches 100 Hz to 500 Hz, we can see that the output voltage and gain starts to decrease, where the gain drops from minus 0.18 decibels to minus 1.62 decibels. This signifies the start of the filter reducing higher frequencies. At 800 Hz and beyond, there is a sharp drop in the output voltage, which is notable from minus 1.62 decibels at 500 Hz to minus 4.15 decibels at 800 Hz. This shows that the filter is actively reducing higher frequencies. From these values, we can then draw the frequency response curve to find the lower and upper cutoff frequencies, taking 0 as our max decibels, minus 3 decibels, which will be over here. Hence, the lower frequency will be 0 Hz, and the upper cutoff frequency will be 700 Hz. We can then calculate the bandwidth, which is 700 Hz minus 0 Hz, which will be 700 Hz. Hence, this stage further amplifies and filters the signal to ensure that the relevant hard sound frequencies, usually below 1 kHz, are amplified while unwanted high frequency noise is minimized. We now move to the last and final stage of this schematic diagram, and this is the audio amp linear gain control. We now touch on IC3. IC3 is LM386N1, which is designed to operate on a single supply voltage. Hence, there is no need for a voltage divider. It amplifies a low-level audio signal suitable to drive a small speaker. Moving on to trimmer port P2. The output at TP4 passes through the trimmer at pin E, which has full amplitude, while pin A and S have zero amplitude of the waveform. This allows users to control the volume of the audio output by adjusting the amplitude of the input signal. C15 and R17 form a Zobel network where it improves the stability of the output by bypassing high-frequency noises. This also helps the amplifier be less dependent on the characteristics of the other loads that could vary due to the high frequencies. C13 is a coupling capacitor similar to the ones before, and it is used to block DC voltage and only allow AC signals to pass through. Lastly, we have the output speaker, where we can listen to the amplified version of the heartbeat. I now connect channel 1's probe to TP4 and channel 2's probe to TP5. With our function generator set at 1 kHz and amplitude of 5 VPP, we can adjust P2 and the output waveform will become saturated. But the final value of the output waveform that we want to attain would be the maximum sine wave without it being cut off, which would be 7.92 volts.